Hello and welcome to this clip on electronegativity, polarity and intermolecular forces. This follows on from the clip on the basics of bonding and will take us through what electronegativity is and how it affects polarity in covalent bonds in particular, and what that polarity means for the ranges of intermolecular forces that result. And we'll summarise it by looking at a worked long answer exam question. So as always, there's a few definitions that you'll need to get down and memorise before we start, so they'll pop up on the screen in a couple of seconds. So this time there's a little bit more to remember because there's actually several things feeding into this topic, as well as a number of different intermolecular forces that result from them. So we'll start by having a look at electronegativity. So at this point you need to get your definition for electronegativity. I'm not going to go through the definitions like I said at the beginning of the clip, so you can either rewind to the beginning of the clip just to write it down, or to get your flashcard or your glossary from the textbook. So whatever you do, have the definition for electronegativity in front of you. So electronegativity increases with proton number, as you can see, across periods. But if you go down groups, you get extra layers of electrons, don't you? So each time you go down one in a group, you get an extra layer of electrons, which means an extra amount of shielding. So therefore the nuclear charge is not as strong at the bottom of a group as it is at the top. So it's important to remember these trends when you're deciding between the electronegativity of two atoms in a bond. So in this diagram we can illustrate it by seeing that the bonded pair is attracted to the chlorine more than it is to the hydrogen. So if you look at very closely the distance between the hydrogen and the chlorine, can you see that the bonding pair is actually slightly shifted more towards the chlorine than it is towards the hydrogen? So we say that this has a dipole, and what we do is we write our partial negative and partial positive charges in. We call it delta plus and delta minus. So basically delta is this symbol here. It stands for the letter D in small case in the Greek alphabet. So therefore delta plus is going to be a slightly positive charge, and delta minus is going to be a slightly negative charge. So when you've got this drawn on a bond between two atoms, you can tell that you've got a dipole. So in fact, because the chlorine is more electronegative than hydrogen, always, this is now said to be a permanent dipole. So you can see how I've added that into the definition, a little explanation in the bottom left hand of the screen. So it's said to have a permanent dipole. So this leads to something quite interesting when we look at hydrogen chloride in a liquid form. So if we liquefy hydrogen chloride gas, so we get something called a permanent dipole-dipole interaction. This is an example of an intermolecular force. It's not quite a bond because there's no electrons being transferred and there's no electrons being shared, but there is an electrostatic attraction between one end of the hydrogen chloride molecule, the delta minus chlorine end, and the other end of a neighbouring hydrogen chloride molecule, the delta positive hydrogen end, and that's signified by the little dotted red line that you can see in this diagram. So this animation that you can see at the moment shows the tendency of the electron density to move towards one atom compared to the other. So in this, you'd expect the chlorine to be here, and the hydrogen to be there. So therefore, this will be the delta positive end, and this will be the delta negative end. And the purple cloud you can see is where we think the electrons are going to be most densely populated, or in other words, the bonding pair. So bonding pair of electrons. Okay, so now we've introduced the idea of intermolecular forces. This isn't the only type of intermolecular force that we can get. So we're now going to look at something called hydrogen bonding. So hydrogen bonding is a particularly strong type of permanent dipole-dipole interaction. It's based on the same idea that we talked about on the last slide, but it has several specific criteria that you must have. So you must obviously have hydrogen, otherwise it wouldn't be called a hydrogen bond. The hydrogen must be covalently bonded to nitrogen, oxygen or fluorine, because there's a very high difference of electronegativity between hydrogen and those three atoms. If you're not sure what I mean, go back to the previous slide and have a look at the electronegativity on the periodic table, and you'll see that N, O and F are in the top right hand corner and hydrogen is in the top left hand corner. So there's a large difference in electronegativity between them. That means the attraction between them is going to be stronger than a normal permanent dipole-dipole interaction. So the final piece of criteria is that the electronegative atom, the N, the O or the F, has to possess a lone pair. So these diagrams show you exactly how to draw a hydrogen bond to get the marks in the exam. So three things to make sure of: the lone pair or pairs on the more electronegative atom, that is nitrogen, oxygen or fluorine, the correct partial charges, and a dotted line to actually represent the hydrogen bond. Don't just do the dotted line, actually label it hydrogen bond like these diagrams have done. That way you can guarantee at least 3 marks on this. So there's a third type of intermolecular force called an induced dipole-dipole interaction. These are quite weak, but they're very common. They take place in virtually all, or they do take place in all covalent compounds. So what you've got to remember is these will be happening all the time. Then in addition, if you have the correct criteria, you might have a permanent dipole-dipole interaction happening as well. And if the difference in electronegativity is strong enough, matching the criteria for a hydrogen bond, you'll have hydrogen bonds taking place. So London forces is the name we use for our exam specification. You might come across them online if you were to look it up on the open internet as van der Waals forces. This is an older name for them. We actually now call them London forces because van der Waals forces are used to describe any dipole-dipole interaction. These are induced temporary dipole-dipole interactions as opposed to permanent. So let me take a moment to explain this for you. So if you look at the animation, you can see that this is similar to the animation in the previous slide, but this time we're looking at molecules where the bonds are not polar, so therefore there's not a big difference in electronegativity. But can you see how when they get close to each other, there's a slight shift in the electron density, very slightly, between them. So in other words, what's going on is that at any given time, the electrons tend to drift around the atom. They don't just stay in their shells, they stay in their orbitals, but what they do is they tend to drift around a bit, and the bigger the atom, the more electrons there are that are present, so the greater the London forces that you can get. So at any given time, if you get an atom, for example, that has electrons in it, evenly distributed, and another atom nearby that also has electrons evenly distributed in it, if that's step 1, in step 2 what might happen is just by chance, in our first atom on the left, the electrons might suddenly drift to the right hand side. That creates a slight dipole across the atom. So what happens now is the right hand atom, the electrons there are repelled. So they also move to the right hand side on their atom, again giving a slight dipole. So this now gives a attraction, very briefly, between the two atoms. So finally, if the electrons start to drift back to their original positions, like so, the attraction now breaks, because what's happening here is there's no dipole across the atoms. So no dipole at the start. You get an induced temporary dipole, which then breaks automatically at random, and you get no dipole. So these are essentially switching on and switching off all the time. So the bigger the atom, the more electrons you have, and the stronger the London force. So this is an important consideration when we're looking at things like boiling point and melting point. In fact, all intermolecular forces, whether they're hydrogen bonds, whether they're induced dipole-dipole interactions, or whether they're permanent dipole-dipole interactions, they all have a bearing on boiling point because they add to the amount of energy that has to be used to overcome them to separate the molecules out. So before we go on to start looking at giant structures, let's look at one more type of bonding you might have heard of, and that's called metallic bonding. So before we go any further with this, let's have a quick look at the effects that some of these differences in polarity in bonds have on the nature of a molecule. So it's important to remember that different molecules exhibit different characteristics to different extents. It's not just simply one is ionic and one is covalent. There's a range of characteristics that go from very ionic to relatively completely non-polar. So it depends on electronegativity, like we said. So if a molecule or a lattice has a large electronegativity difference between the individual ions, then it's going to be an ionic or a full ionic bonded. So in terms of charges, the sodium would be fully positively charged and the chloride ion would be fully negatively charged. What would happen in the middle between hydrogen and chlorine is the chlorine is more electronegative, so the electrons will tend to sit a bit more closer to the chlorine, giving the partial positive and partial negative charges. So that's called polar covalent. If you look at chlorine, even though individual chlorine atoms are very electronegative, they're the same degree of electronegativity as each other. So there's no difference in electronegativity between them. So it's important to remember that you get different variations on this theme, and think about the electronegativity difference between individual atoms and individual bonds before you decide whether a molecule itself is polar or not. So the next thing to look at is, what does a polar or a non-polar molecule mean? Well, we've done the idea of simple molecules such as HCl. What about molecules that do have polar bonds in them, but the molecule itself is non-polar overall? How does that work? So if we take a molecule such as methane, if you haven't done shapes of molecules yet, don't worry about why I'm drawing it in this particular way. If you have done shapes of molecules at this point, I'm obviously drawing it as a tetrahedron. So this is our methane molecule, CH4. If we were to do the dipoles, in each of the bonds, how would this work? You'd have carbon being slightly more electronegative than hydrogen. Now I'm doing this because a lot of people in lessons say this kind of thing to me, why do you consider methane a non-polar molecule? Why do you consider the carbon-hydrogen bond a non-polar bond? The reason is because there's actually relatively little difference in electronegativity between the two. So if we were to now swap all of those hydrogens for chlorines, like this, you now have a bond where there's a large electronegativity difference between carbon and chlorine. So the dipole is much more pronounced. You'll see I'm actually drawing the partial charges as a little bit bigger in this diagram than they are in the other one. You don't have to do this. You don't actually have to worry about the size of your delta minus or the delta pluses. I'm just doing it to try and illustrate a point. So although the carbon-chlorine bond can behave individually as a polar bond, what actually happens here is the direction in which the dipole acts. They all act in different directions, so they cancel each other out. So this is considered to be a non-polar molecule because the dipoles cancel. So it's worth looking out for other examples of this type of thing. So how about a slightly trickier version? Let's now look at carbon, fluorine, and then 3 chlorines on it. On this one, they all have a dipole. Oops. But the fluorine has a much stronger electronegativity than chlorine. So by far the strongest dipole acts in that direction, and the other dipoles are much weaker by comparison, hence the smaller arrows. So therefore CFCl3 is polar. So because the carbon-fluorine bond is more polar, like we just said, has a greater polarity than carbon-chlorine, CFCl3 is actually polar. So now let's try an exam question. So let's have a look at this question, which is worth 4 marks. So let's look at the first piece of information that it actually tells us that might be useful. It says it contains, or hydrogen chloride and fluorine contain the same number of electrons. And what it asks you to do is to explain why there's a difference in the boiling points. And it says you should refer to the types of force acting between molecules and also the relative strength of the forces acting between molecules. You should use appropriate technical terms spelled correctly. And they offer 4 marks. So let's have a look at the first piece of information. It says they contain the same number of electrons, so that means that they don't, the difference between them is not only due to London forces. In other words, it's not that one has more London forces than another. If you remember about London forces, they're determined by the number of electrons that are available. If there's more electrons because you've got a bigger atom, then you'll have more London forces. So it's not a massive difference in the number of electrons. There's no difference, in fact. So London forces are not the main reason for this difference in boiling point. So we have to think of other intermolecular forces. So let's do hydrogen chloride first. So I know I haven't discussed the actual intermolecular forces in fluorine yet, but the fact that hydrogen chloride has a much higher boiling point, I've just spotted up in my question, I've said hydrogen boils at minus 85, and I meant to say that hydrogen chloride boils at minus 85, so I'm just going to go and change that. So fluorine, although individual fluorine atoms are very, very electronegative, in fluorine they're the same as each other, so the two atoms are identical, so their electronegativity is going to be identical. So therefore, it's going to be London forces that are occurring only in fluorine. So in terms of our marks, we've made a comment about the type of intermolecular force in each case, and we made a comment about the relative strength of the forces in each case, so that gets us our 4 marks. So hopefully again you found this fairly useful. Please don't hesitate to rewind back and check anything over again, or come to one of us at college to double check, or come to a subject extension. Thanks again for listening, and see you soon.